Hi everyone, myself Navyatha, working as Assistant Professor in the Department of Cyber Security and Data Science in MLR Institute of Technology. Today I am going to discuss about the topic B+Tree, a dynamic index structure insertion. And the insertion is nothing but the operation that we use to perform in B+Trees. The overview of my presentation includes about B+Trees and the operation that we use to perform on insertion, B+Trees. Okay, so we have to perform insertion, deletion and search operation. We can display the elements also. After performing all these operations, we can perform deletion and about display also. We can perform displaying the nodes after performing all these operations. Let us discuss what is B+Tree first. It is a file organization to organize a file in DBMS. The records are sorted using the primary key to conform with the key value pair rule. It is a tree-like structure. So it's just like what BST, binary search tree. The basic difference of binary search tree and B+Tree is nothing but binary search tree contains only 2 children per node. But here B+Tree we have any number of children. Okay. And here the records are stored in a sorted manner. B+Tree file organization is much similar to BST, as I said just now, but it can have more than 2 children. So B+Tree can have more than 2 children. The leaf nodes of B+Tree file organization contain all the records. Whatever the actual data, that data will be stored in the leaf nodes only. All the internal nodes will act as the pointers to these leaf nodes. Okay. And the middle nodes, that nothing but the internal nodes, contains only pointers to the leaf node. It doesn't carry any records. Whatever the nodes that acts as internal nodes doesn't have any actual data. For example, let us consider this is a node. Okay. And these are the nodes and these are the leaf nodes. These are the leaf nodes. Here the last level is nothing but the leaf nodes which contains actual data. Actual data. That means whatever the records that we used to store, those records will be stored at the leaf level. And these are nothing but which we called as internal nodes, and the initial node is nothing but the root node. Okay. So from the searching will be done from the root node. Insertion, deletion, whatever the operation that we used to do will be done from the root node in B+Trees. So what are the rules that we must follow to construct a B+Tree? So data is present in the leaf nodes only. Whatever the actual records, those data will be present in the leaf nodes. Tree can be left biased or right biased. So here sometimes we used to split the node. If the node becomes overflow, then we used to split the node. Then to split that node, we have to follow either the left biased or right biased. This will be explained very clearly while considering example. Okay. Left subtree must be less than the root node and right subtree will be greater than the root node, greater than or equal to the root node. Okay. So here, for example, the root node contains 10. Okay. The left subtree must be less than. This is what the left subtree. This is what the left subtree and this is what the right subtree. This is right subtree. This is left subtree. Right. So, the left subtree must be less than the root node and the right subtree must be greater than or equal to the root node. So, here let us suppose the elements 9 is less than 10. So, here after 9 or else let us take here 7. Okay. 7. Okay. So, this is what the left part of the tree from the root node. So, 7 must be kept to the left part. Next, I have to insert 6. Where I have to insert? I should check from the root node. Whether I have to insert 6 is less than 10? Yes, I have to come this node. 6 is less than 7? Yes, I have to insert to the left part of the tree. So, here 6 I have inserted. Now, I should insert 9. Let us suppose I have to insert 9. So, where should I insert 9? So, first I should compare whether 9 less than 10. Yes, I use the left pointer. Okay. Whether 9 is less than 7? No. So I should go for the right pointer. Here I should place. You observe one thing, that all the elements in the left subtree which are less than the root node. So in this manner we used to place the elements or records. Okay. In the same manner, here I should, if at all I want to insert 15, if at all I want to insert 15, where should I insert? So from the root node I have to search whether 15 is less than 10. No. 15 is greater than 10. Yes, it is greater than. So I should use the right side pointer and I have to insert 15 here. Now I want to insert 12. I want to insert 12. Okay. So where should I insert? So 12 is greater than 10. So I supposed to go for the right pointer. Okay, right subtree. And I should check whether 12 is greater than or less than 15. 12 is less than 15. I have to choose the left pointer and here I should place 12. Okay. Now I have to insert 16. I want to insert 16. Where should I? From the root node I need to check. So 16 is greater than 10. Yes, I should choose the right pointer. 16 is greater than 15. Yes, I should. And here I can insert 16. Observe all the elements in the right subtree which are greater than the root node. In this manner, we used to place the records. Okay. So, if order of tree is M, here these are some of the conditions that we should follow to construct or to maintain the balance in B plus trees. So, if the order of tree is M, order is equal to M, then maximum children must be M itself. Minimum children is equal to ceil of M by 2. Right, ceil of M by 2. Maximum keys can be M minus 1. Minimum keys ceil of M by 2 minus 1. Let us discuss with a simple example. That means if at all, if M is equal to 4, let us consider M is equal to 4. That means order of tree is 4. Okay. So, maximum children can be how many? Maximum children 4. Why? Because M only. Okay. How many we can expect the minimum children? Minimum children means what? Ceil of 4 by 2 is nothing but 2. So, minimum children must be 2. We have to maintain minimum 2 children per node. Okay. Maximum 4 children. Next, maximum keys. Keys means a node contains how many data elements. That is what here key. Here the data elements are nothing but the key attributes. Okay. So, maximum keys per node. So, for example, M minus 1, that is 4 minus 1. Maximum keys how many? 3. Okay. Now, minimum keys. Minimum keys means ceil of 4 by 2 minus 1. That is 1. Okay. So, 2 minus 1, that is 1. So, minimum keys we have to represent, we have to maintain 1 key. So, here what is 4? That is the order we should maintain. And if at all a node, this is what the initial node. How many keys we have to maintain? Maximum keys per node? 3. Okay. So, that means we can store 3 elements in that particular node. That is what the representation of keys here. This is what key 1, key 2 and key 3. How many 3s? 3 keys maximum. Okay. Minimum key that we should maintain. Minimum key. Compulsorily we should maintain minimum 1 key per node. Okay. That is what the rule. Minimum children. Minimum children 2. Maximum 4. How we can able to get 4? Here this is what one pointer, this is what another, this is what another pointer, this is what another pointer. Okay. Let us suppose consider a node like this. Okay. This is what key 1, this is what key 2, this is what key 3 and okay. Why? Because we have only maximum keys 3. Out of these 3 keys, how many children can be possible here? See, 4. If at all we have M keys, then how many pointers we can use? M plus 1. 1 pointer extra. Okay. So, here how many maximum children? 1, 2, 3 and 4. That is what the representation. Okay. Let us deal these things with a simple example. Okay. So, here I want to insert these many elements of size of order 4. Okay. I want to insert these many elements. So, by considering the above rules which I have mentioned, order which I have given m is equal to 4, maximum children must be 4, minimum children, seal of m by 2, 2, 3, maximum keys, minimum keys 1. So, let us insert one by one. Okay. This is what my root node. First of all, how many keys are possible here? How many keys? How many keys here? See, 3 keys. Maximum keys 3. Okay. So, 1, 2 and 3. I can insert 3 keys per node. My first element is 1. So, here I have to insert 1. 1 has been inserted. Next, what is the second element? 4. So, here we have space, right? So, I can insert 4. Okay. Next, 7. Here I have space. One more node. 7. I can insert 7. Okay. The next element is 10. The next element is 10. Where should I insert? One thing you have to remember, we have to insert the nodes in a sorted manner. Whatever the data element we used to get, first step is we used to sort those data elements. Okay. Whatever the data elements given, our primary thing is we used to sort those elements. By using any sorting technique, we can sort those elements, and after sorting only we must insert the elements sequentially one by one. Okay. So, we have inserted 3 elements. The next thing is I have to insert 10. But the maximum keys per node is only 3. I have inserted already 3. Where should I insert 10? So, we need to split the node. Okay. So, we need to split the node. Here, we should insert 10 after 7 only. This is what my order. The middle element must be sent to the upper node, index level. Okay. So, now what are the middle elements here? Why? Because we have 4 keys here. We need to insert this one also. We have 4 keys. What will be the middle elements? 4 and 7. Okay. These 2 are the middle elements. From these 2, we can consider either 4 or 7. If at all I consider 4, then it is called as left biased. Okay. If at all I consider 7, that is what the right part, then it is called right biased. So, if at all I used to consider 7, right. So, 7 can be taken as the root node. 7 can be taken as, now the 7 can be taken as the root node. Why? Because I need to shift the 7 to the index level. Okay. So, 7 can be taken as root node, and the left part of the 7 will become, see here, 1 and 4 will be inserted here, left part, and the right part of 7, right part means this pointer only, right? Left part is here, right part is here. So, the right part of 7. So, what we have to insert here? 7 as well as 10. We have to insert the element also. Why? Because the actual data must be stored in the leaf nodes only. So, we have to insert 7 also here. 7 and 10. Okay. Again, one place has remained here in this tree. Okay. This is what the way you have to insert the nodes. So, whenever an extra node comes and the bucket is full or else the node is full, then we need to split. At this moment, we used to represent the left biased or right biased. So, here this I have considered as right biased. Okay. So, now I have inserted 10 also. Now, what is my element? 17. 17 I have to insert. Okay. So, where should I insert 17? Here itself I can insert 17. Why? From the root node we need to search, right? So, 17 is greater than 7? Yes, it is greater than. So, I should choose the right pointer here. Okay. Then I can insert 17 here itself. Why? Because the place is there in that particular leaf node. 17 I have inserted. This is also completed. Next, 21. Okay. 21. Where should I insert 21? 21 I used to compare with 7. It is greater than. Here I have to insert 21. Okay. Then there is no place. Then again I need to split this node. And I have to shift the middle element to the index value. So, here by inserting 21, what is the middle element here? 10 and 17. So, in the first time when I am splitting, I used to choose the right biased. So, for every splitting from first to till the end insertion, I have to choose right biased only. Okay. So whatever the step you have chosen for the initially, that step must be continued till the end. So first I have chosen right bias, then I should take the right element. So what is the rightmost element here? 17. This must be shifted to the index position. So what is the node that I used to get here? What is the node? So 7. Okay. 17 I have shifted here. Okay. To the left part of 7. What is the value here? 1, 4. Okay. To the right part of 7. What is the value here? 7 and 10. Again one more. And to the right part of 17. To the right part of 17. What are the values here? 17 and 21. 17 and 21. So for each and every node, maximum key is 3 we can insert. So that is the reason here I have inserted. Even though I shifted 17, 17 become now index, and for actual data representation, here I used to represent 17 in the leaf nodes also. Okay. So this is what till now. We have inserted 21 also. Next I need to insert 31. Next I need to insert 31. So where should I insert? I used to compare whether 31 is greater than 17. Yes, it is greater than. So I can come to the right part of this 17 and I can insert 31 directly here. Why? Because there is a space in the leaf node. Here you must consider this part is nothing but the leaf nodes part. This is what the index value. That is what root node. Okay. So 31 has been inserted. Next, what is the value that I am going to insert now? 25. 25. So where should I insert 25 here? See, after 21. Why? Because we need to insert the data in a sorted manner. That is the reason here 25 must be inserted after 21. So what is the element that I used to shift to the index value? What is the middle elements here? 21 and 25. These two are the middle elements, right? So here I have chosen already right biased. So 25 must be shifted up. Okay. So after shifting 25, then I can able to split the node like this. Okay. See, after 25, the 25 will be kept here and the 31 will be stored in the right part of the 25. Why? Because it is greater than 25. So in this manner, I used to split the node. Okay. So this is what the tree after inserting 25. Next, I need to insert 19. Next, I need to insert 19. So where should I insert 19? So here, it is greater than 7. Yes. Okay. Yes, it is greater than 7. And let us check one by one the root node. What should I insert? 19. So it is 19. If at all I used to insert 19 here, then I used to violate the B+T rule. Why? Because see here 17 left part. This is what the left part subtree of 17. That must be less than 17, but 19 is greater, so we must not insert 19 here. Okay. So where we should insert 19? Here after 17. Why? Because 19 is greater than 17. So here we should insert 19. That means, so this node will become 17, 19 and 21. Here we should insert 19. Okay. So here we have inserted 19 also. Next, 20. So in this tree, where should I insert 20? At this position. At this position, I should insert 20. Okay. So what should I do now? I have already 3 keys, maximum keys 3 filled. So I should split this node and I should move this 20. Okay. Why? Because I have chosen right biased. So I should move this 20 element to the index value. So if at all I used to move 20 element to the index value, the position will be here. The index value also filled with the maximum keys. Okay. Again, what we should do? Here also the splitting must be done. What is the middle value here? See 17, 20. As I have chosen the right biased, the 20 will become the root node now. So 20 will become the root node. Okay. So 20 will become root node. The left part of 20 will be 7, 17. Okay, left part of 20 will be 7, 17 and the right part of 20 will be actually 25. Here we should not insert 20. Why? Because here this is what the internal node, right? This is not the data leaf. That means the actual record. Okay, it acts as a pointer. Actual records must be kept in the last leaf nodes. So that is the reason here I may not insert the value 20. Why? Because this node is an internal node. Okay. So to the left of 7, here I can give 1, 4. To the right of 7, here I can represent 7, 10. And to the right of 17, here I can insert what? 17 and 19. Okay. Now, as 20 is the root node, here to the left of 25, here what I should insert here? 20 and 21. Okay. To the right of 25, here I should insert 25 and 31. Why? Because here the root node which I have chosen is 20. Left part, left subtree must be less than 20. Right part must be greater than or equal to 20. That is the reason here I used to split 20, 21 to the left of 25. Okay. So, in this way we used to insert 20. Next, 28. Where should I insert 28? See, 28 is greater than 20. That is what? Right subtree. 28 is greater than 25. Okay. That too to the right part. And here, where should I insert? After 25, 28, then 31, which is already there. Okay. So, in this manner, I used to insert 28 also. Okay. Next, 42. Where should I insert 42? See, 42 is greater than 20 to the right part. 42 is greater than 25 to the right part. Here I should insert. So, there is no space. Again, I need to split this node. Okay. So, what are the middle elements here? 28 and 31. So, what is the element that I should move to the index part? That is nothing but we have chosen right biased. So, right element. That means 31 will be moved here. Okay. 31 will be moved and here 25, 28 will be kept and to the right of 31 here 31 and 42 will be inserted. Why? Because 42 is greater than 31. So, in this manner, I can able to insert all the elements by splitting the nodes and by considering left biased and right biased. So, in this way, we used to insert all the elements, all the given elements. Thank you.